defines an ideal. So in principle, we can transform every geometric problem about algebraic varieties to algebraic questions about this polynomial ring. And then the next step was, why stop at maximal ideals? Let's consider all the prime ideals. So let's agree to consider irreducible algebraic subvarieties as also as points. Okay, and we generalize them. We extend the Zariski topology in an obvious way. So instead, analysis the topological space of all prime ideals. So close subsets are like this. This is the Zariski topology. And once we've done that, why stop at that? Now we can do this with any ring, any commutative ring with unity. Sometimes we require the ring to be Noetherian to make it look like usual geometry, but now we can consider for me, ring always means commutative with unity. We can consider the set of prime ideals. When we define the Zariski topology in this way, and we can do geometry. So that's almost all I want to say about general scheme theory. I'll comment on what's the interest of doing this, what are the advantages of scheme theory. So the first big advantage is generality. You know, when I was starting to study mathematics in Russia, there was a kind of saying that the goal of mathematics, or the goal of every mathematician, is to reduce all mathematics to one formula. This is maybe too much, but well, I mean, the reason we like so this is maybe too much to quote, but the reason we like abstraction and generality is not just for their own sake, but it's nice to, you know, instead of having 10 different theories and 10 different areas of mathematics, it's nice to be able to state this just a single theorem. So you see here, this ring A, this could be a polynomial ring over any field, in particular fields of positive, not only over R or C, but could be fields of positive characteristic, or it could be arithmetic, either polynomial or normal power series ring over Z, or with numbers, or it could be a ring of conversion power series in the situations when we have a norm. So this allows us to fit many very different subjects of mathematics, like algebraic geometry, local analytic geometry, or number theory. To some extent, we can prove theorems, the same theorems by the same methods. For example, many of the recent classes of number theory, whether it's heard of Fermat's theorem or Voltig's proof of Gauss conjecture, would be unthinkable without geometric conjecture. So a large part of the proof is doing algebraic geometry in this sort of case. Okay, the second advantage is, which I won't talk much about, is nilpotent structure, nilpotent structure. So when I consider an affine scheme like this, the ring A is part of the data. So I don't think of it just as a topological space. I already think of it as a pair. So for example, these two rings defined as a topological space, the spec is exactly the same, but we distinguish them in scheme theory. That's important. For example, there are examples in Hartshorne when you deform a reduced scheme, you obtain something non-reduced. So certain natural operations naturally lead to considering non-reduced schemes or rings with important elements. So that's an extra richness. And the main reason why I'm telling all this, what I'm going to use is the notion of generic point. that was one of the weaknesses of the Italian school. That very often in algebraic geometry we make arguments by taking a sufficiently general point in an algebraic variety. And that's the way the Italians were doing it was not rigorous. And it's not always clear what it means, sufficiently general point, and this led to mistakes. So there were some kind of intermediate notions because I escaped there more rigorous or generic points, but with Grothendieck's theorem schemes, this became completely rigorous canonical, so let me explain that. So
excuse me, you have a very loud voice, but it's insect.
Oh, sorry, Is it better? Yeah. Okay, so let's consider a fine scheme like this, let A be a ring, and let P be a prime ideal of A. So we know that P defines, so V of P is an irreducible closed subscheme of spec A. But also remember, at the same time, remember that P is a point in spec A. So what happens is that, and this is immediate from definitions, is that the closure of this one-point set consisting of P is all of P of P. Okay? So this typically, unless P is the maximum ideal, typically this one-point set is not closed, and its closure is all of P. But by definition, so we say that this is called a generic point. So what in Italian geometry was this vague notion of taking a sufficiently general point on the variety. In scheme theory, it's completely canonical, it's a unique, or irreducible closed subscheme, but it's a unique generic point. And that's plays the same role that in the old days people would just choose a general point in the variety. And so the reason I was telling you all this is because the definition I'm going to make now, the center of valuation, on a variety need not be a classical point, it might be a irreducible subvariety. It's only a point in the sense of schemes. But I guess more general, when I was a student, there were many people, old and young, who were afraid of schemes. And I also know that there's nothing to be afraid about, nothing to be afraid of. It's like everything else in mathematics, there's nothing. No such thing as too abstract or too kind of completely. Just learn the definition, do examples. It's not good to cut yourself off from any part of mathematics because it's too abstract. Okay, so now let's come back to relation theory. So that the field will be relation. And that R can be a local domain. So no zero divisors containing K, whose field of reference is K. This is going to be our bridge to birational geometry, the use of valuations in birational geometry. So we say that mu is centered at this local ring if the local ring is birationally dominated by the valuation. But remember what this means, right? What does birational domination mean? It means that, first of all, that R is contained in R mu. That's the same as, so let me just, so this is this, R is contained in R mu. That R mu is the set of all elements on which the variation is positive. So this just means that my variation is non-negative on R. And the fact that the maximal ideal is the set of all elements that is restricted. So the fact that it restricts to M just means that my variation is strictly positive on the maximum. Okay. So let me maybe do an example. an example for. So what does it mean to say that evaluation is centered at this local the polynomial is localized at the origin? Well, it simply means that, so here, mu is centered R, if and only if right, so to be centered at this local means that first of all the values of U and B should be non-negative, but in fact since the maximal ideal is generated by U and B, they should be strictly positive. That's equivalent to being centered. So that's the case for study. And the next topic is to connect valuations with birational geometry. So we want to know what happens under blowing up. That's part of the philosophy that valuations are objects which are associated to the entire field of rational functions, not to a particular birational model. So we want to know what happens under blowing up. So let me define, this has been defined many times, particularly yesterday in the discussion session, but let me quickly define the blowing up of point in the plane, maybe point in space, and then later I'll give a more general definition of generalities, which is a little bit more general than what they defined. It follows the same lines as what they defined yesterday, but just a little bit more general. Okay, so let's start with blowing up. Blowing up point in the plane. So remember, in our new language, the plane is the stack of the polynomial ring. It's a set of all prime ideals. This polynomial ring. The origin is the maximal ideal generated by U and B. Blowing ups are birational projective transformation. Birational means that it's an isomorphism of the local set. So it means that I remove a subvariety, which is called the center of blowing up, in this case the point, and I glue in some other subvariety in its place, which is usually called exceptional set or exceptional device. So in this case, the center of blowing up is going to be the origin. I consider the set of all straight lines which pass to the origin. This set of straight lines is parameterized by P1 over K. And so I remove the origin and I glue in P1. P1, which parameterizes these lines. Yeah, Bernard drew a much better picture yesterday, but no. So I replace the origin by P1, and everything else remains the same. Okay? So for example, if K is equal to R, this is a very bad picture of a Möbius span. Right? So you have a line which goes around once. So P1 is a circle, so you have a line which goes around once. And so of course we're doing algebraic geometry, so we're interested in algebraic equations. So here we start with a coordinate ring K of UB. Upstairs is no longer affine. There are two affine charts. And the coordinate rings of those two affine charts are usually written like this. Okay, so U over B is, this parameterizes the slope of the line, so this is the coordinate along the exceptional divisor. And V is the local equation of the exceptional device. So this is V1 is the exceptional divisor. Or you can do the same. There are more general blowing ups which we'll consider later. For example, let me just do one more, which is blowing up. Let's say Euclidean space, n-dimensional Euclidean space, also the origin. So this looks very similar. We start out with Euclidean space. Here, the set of all lines passing through the origin is parameterized by Pn minus 1. So I remove the origin, and I glue in Pn minus 1. So, but otherwise the picture is very similar. So yeah, it's more than 2 dimensions, but so upstairs all the lines which used to pass through the origin upstairs all disjoint, and again algebraically. So this is covered by n affine charts. The equations are the following. The affine chart number I looks like this. So again, here, those n minus 1 coordinates are coordinates along the exceptional divisor, and ui is the local equation of the exceptional divisor. We'll do, and as was explained yesterday in the discussion session, maybe a better way of thinking about this is that what we do is we remove the origin, we look at the map, in this case into one-dimensional projective space, which maps every point on the line to the corresponding point in the projective space, the slope, and then we take the closure of the graph. And so that has the effect of gluing in this entire exceptional divisor. Okay, so I'll explain this in more detail later, in more general, I think. I guess one advantage of being chairman is I can give myself as much time as I want. I have to stop myself. So let's continue with our quest in classifying all valuations of the plane. So let's, I guess this appeared in the talks of Felipe. So if you have, so I feel this is usually going to be this. If you have any valuation of this field, if you have a projective variety like projective plane, then maybe I'll leave it as an exercise. Then there's definite, so let's assume that my valuation vanishes on K. So if I look at the projective plane, there exists a point at which the variation is centered. I'll leave this as an exercise. So you use any variation. There exists a unique point in the projective plane such that C. But let me say this in more naive terms. So I start with an arbitrary valuation. If it happens that, what does it mean to be centered at finite plane? It just means that the valuation is non-negative on U and V. So if it happens to be negative, I just replace U by 1 over U. So if the valuation happens to be centered at infinity, I'll just replace U by 1 over U or V by 1 over U. So in this way, it's replacing necessary. Assume that so once I assume that the valuation is non-negative on the polynomial ring, then it's immediate that there is a unique center, right? Because what is the center? It's just I take the maximal ideal of the valuation ring and I intersect with the polynomial ring, I get a prime ideal. So then by definitions, it is centered at mu. Okay. So let's analyze what are the possibilities. So this is a prime ideal, this element of spec. This could be the zero ideal, right? So this one is, this could be the zero ideal. This is so-called trivial valuation. evaluation with value group 0, which assigns 0 to everything. I don't know why Zariski is writing, for example, in Zariski Samuel, he's always obsessed with the trivial evaluation. I never quite understood why he always makes it and considers the special case, makes some special discourse. I don't know if it's really necessary. Anyway, we should not forget about that. And another possibility is there are not too many ideals in the polynomial ring. Could be either the zero ideal, prime ideals, or a principal ideal generated by irreducible polynomial, or a maximal ideal. There's not much more that can happen. So this would be a principal ideal with an irreducible polynomial. With an irreducible. But then this is our old friend. This is like a t-adic relation. So this is the is the affine relation. So that means that every polynomial g can be written uniquely in this way, where f does not divide u, and we set mu as g to be n. It's similar to the first example I gave. Or if you like, we consider the divisor, the curve defined by f, and evaluate the order of the generic point here.
There's something you define center, it's a different documentation, it says centered at the local ring, and there you're saying centered at the maximum of the prime ideal. So the center of the.
Yes, so the prime ideal is the same as a point, right?
Okay.
So we sometimes we say either centered at the point or centered at an ideal, or if it's a local ring, when we say centered at the local ring, we mean centered at the maximum ideal. Okay. So it's just the terminology. That's just the terminology we uses. And the last remaining possibility could be a maximal ideal. So let's assume for simplicity that A is algebraically closed. So this would be a maximal ideal. Remember I said yesterday by Stellensatz, that means that that means that it must be the form u minus a b minus b. And so changing coordinates, let's assume that my evaluation is centered in the origin. Okay, so changing coordinates. But now my main interest is to see what happens under blowing up. Okay, so what's the relation between federations and blowing up? So let's consider, let's say, x prime g, the blowing up. Of the origin. So this is exactly the transformation I defined there. Now, proposition, let's say proposition. There exists a unique point, C prime and x prime, such that mu is centered at C prime. Okay. And that's not hard to prove. Well, okay, let's prove it. So our first task is to decide which of the two coordinate charts the center belongs. It could belong to both. But that's kind of obvious because you know that evaluation rings we have either u over v or v over u belongs to the evaluation ring. In other words, one of the two has smaller ordinal value than the other. So the one that has smaller value I put in the denominator. Okay, so say u over v belongs to the variation ring. But then that means that the whole coordinate ring is contained. So K, V, U over V is contained in the variation ring. And now it's immediate. The center is nothing but the intersection of the maximal ideal with this polynomial. Then C prime is nothing but the intersection with that. So again, but this is the whole reason for telling about scheme theories, because this C prime might be given by a maximal ideal or by a prime ideal. So again, there are not too many options, because this C prime, actually I should be a little bit more precise here. C prime is not only an X prime, but it's an pi inverse of the maximal ideal. Okay? So it's a point that maps to the origin. There are not two, oh, I shouldn't have erased it. Well, let's pretend this is the plane. Okay, so there are not too many options. It could be in two dimensions, either the entire exceptional divisor or a closed point on the exceptional divisor. So what does it mean for the variation? How do we tell from the variation? So again, case one. If it's the entire exceptional divisor, there's only one valuation that does this. It's the valuation which evaluates the order at the exceptional divisor. And that's the ematic valuation. So the first case is that where so the ematic valuation is just the usual order of the polynomial of the origin. And when you blow up, we can write this down. So after blowing up, let's call the new coordinates v prime and u prime. Okay, so let's write this out in new coordinates. So this polynomial is it's u. So u is the same as u prime times v prime, and v is the same as u prime. So you see what happens here. What is the minimum alpha plus beta when it's just here upstairs just a v prime adding order. It's just the divisibility by v prime. U prime no longer plays a role. So this is in other words, this is a maximal n such that u prime to the n divides. So quite whatever is f divides. So this is our old friend. This is the valuation which measures order of vanishing of all along the device. Okay, and that uniquely determines. Okay, so here, so that this valuation obviously has the entire exceptional divisor as the center. Case 2. So if nu of u is strictly greater than nu of v, then, well, I follow the recipe. Then C prime is just the maximal ideal at the origin upstairs, right? Because this is characterized by the fact that this point is characterized by the fact that both coordinates have strictly positive values. It's a unique such point. So this is speaking origin upstairs in one of the coordinate charts. And of course, symmetrically, nu of u is less than that means we're taking the origin of the other coordinate chart. And finally, case 3. The only remaining case, again, let's assume that the field is already closed. So case 3 is that there is existing, so mu u equals mu of v, and so here we also have mu of u equal mu of v, but the remaining case is the following: is there exists a mean constant, non-zero constant, such that mu of u minus cv is strictly greater than mu of u. So in other words, mu of u over v minus c is strictly greater than mu of u. And so this constant is what determines the center. This so you should think of this constant as the coordinate along the exceptional divisor. It picks up on the unique point, which is the origin, which is not the origin of either of the coordinate charts. If c is different from 0. So you should think of c as the coordinate along the exceptional divisor, which picks out the center. Now we've covered all the possibilities. But from this we can draw the following conclusion, that unless my evaluation was the American evaluation, unless we're in case 1, we can iterate the process. Unless we're in case 1, that means we have a closed point, we have a honest point in classical sense, then we can blow it up again and keep going. Okay. So unless is m, we can iterate the procedure. And so, conclusion, for every variation centered the origin, we can associate a sequence of point blowing ups. Yeah, this is the Canadian, you never know how to say this. This is the Canadian declaration, how we form plural blowing up. Yep.
In the case 3, when you divide by b, the value of the u over v minus c is positive.
Zero, sorry. That's what makes the say. That's how the variation picks out the center. It's the unique point where both coordinates have strictly positive value. Right? V already has positive value. We need to find a point with this has positive value. The sequence will be finite origin. Okay, and it turns out that the sequence completely determines the variation. Let's do an example. Let's sort of pick up the old example where we sort of constructed the variation step by step, and let's see what it means in terms of blowing ups. Example. So just as before, let us leave it open-ended. Let's start by giving some values and some people in orders and see what happens later. So let's assume that u is 1, u is 2 halves. Let's assume that the first people in order looks like this. The constant is 1 for simplicity. And let's assume that there is let's say 16 over 5. Okay? Let's see what happens. So we can start. The blowing ups. Okay, so the first step we already know. There are various ways to describe this. I guess one of the nicest ways to describe the blowing up and the center pickup space by writing down the coordinates at each point. That tells the whole story. So the first step we already know, the new coordinates are going to be u over v over v. That's because the value of v is strictly greater than the value of u. So this quotient is strictly positive value. So let's try to draw, even though it's hard to draw. Let's try to draw the exceptional divisors. So here, so I have one exceptional divisor, one P1. Okay, let's write down the values. Here we have 3 halves, 1. Here we have, now it's 1/2 over 1. So now it's obvious. Now this coordinate is the one with the smallest value. So after the next blowing up, we'll obtain v over v comma v squared over u. And so we have a new exceptional divisor, which is created. And now my point, my center is at the intersection of the two. Okay. Okay. Now it's 1/2, 1/2. Now it's getting interesting because now the two coordinates have the same value. So what it tells us is that so this is going to be a new exceptional divisor. So in each step I remember the strict transforms of the previous exceptional divisors. You know that blowing up is an isomorphism outside of the center. So for any curve whatsoever, I can take that curve, remove the origin, look at its greenage, its isomorphic greenage, and take the closure. That procedure is called taking a strict transform. So I keep remembering that I'm constructing some more and more complicated projective surface, and I keep remembering the strict transform of the previous exceptional divisor. So here it will give me some kind of combinatorial picture, graph, a dual graph, which appeared already in the talks of Javier Fernandez and Juanita. Okay, so the fact that these two are equal tells me that the center belongs to the latest exceptional divisor, but it's definitely not one of the origins. It could be definitely not one of these two intersection points. It could be either the entire exceptional divisor or some closed point of the exceptional divisor. But because the only way it could be the entire exceptional divisor if in my old terminology, if mu was equal to mu 0. If mu was monomial with respect to u, which is not the case by assumption. We're assuming that there is a key polynomial which has values strictly greater than 3. And so in this case, the center must be a closed point, and which point it is of the exceptional divisor is determined by the constant which I have here. So in this case, the constant is 1, so there's a unique point with coordinate 1, and this is the center. Okay, so here, let me write down the coordinates again. So here it's u over v, and it's dq over u squared minus 1. So you see again, by our assumptions, because we assume this is the coordinate which has strictly positive value. Okay, let's continue. So when we think of this as a kind of first combinatorial package, or that's what Felipe calls user packages. Until now, the procedure was completely combinatorial. It was everything depended only on the value of the monomials. But here, for the first time, there is a constant involved. Could have been some other constant. And so we're done with the first combinatorial package, and we're starting with the second one. Okay. And another way of thinking about this is that these are very small numbers. Another way of thinking of this monomial package is that you see what's happening to the values. So we take the pair of values and replace it by the smallest value, comma, the difference. So this is Euclidean algorithm. So we're doing Euclidean algorithm on these two numbers, which is also the same thing. It's another word for its continued fractions. We're expanding 3 over 2 in continued fractions. And that's why continued fractions appear all over the notes that I distributed. So let's continue a little bit more. Let me give, now the notation is getting very, very ugly. So let me call this U prime. Let me call this Q1 prime, because this is the strict transform of the first key polynomial. And let's continue. So remember now what the values are. This one is still 1/2, and this one is, it's 16 halves minus 3, so this is 1/5. So we start a new combinatorial package, new combinatorial procedure, which until now we were doing Euclidean algebra or continuous fraction of 3 halves. You know, it's a very simple continuous fraction. It's 1. Okay, so that's why if you look at the handouts, there I do the most general case. So this is why, because it's 1, 1, 1. This is why we have one exceptional curve here, one exceptional curve here, and one in the middle. Okay. The next one is going to be, so this is like continuous fraction 5 halves, so that's going to be 2 plus 1 over 1 plus 1, right? So in the next combinatorial package I expect instead of having 3 curves, I expect to have 4 curves. And let's see what happens. Okay, so anyway, 1/2 is greater than 1/5, right? So the next one is going to be U prime. So U1 prime, U1 prime. Okay, so now I have my now I did another blowing up, okay, and now the fact that you see that U prime was the local equation of the exceptional divisor here, so the fact that I'm in this coordinate chart means that my center is not an intersection point with the previous exceptional divisor. Okay, so now the new values are, so this is still 1/5, so what's 1/2 minus 1/5, that's so 5/10 minus it's 3/10, right? I hope I got this right. Okay, so another blowing up. Okay, now this one is, okay, so this one is going to be still 3/10 is still greater than 1/5, right? So the next step is going to be that's 1/10, so it's going to be U prime, U1 prime square U1 prime, right? So this is going to be now 1/10, comma 1/5. So, but now, yeah, so now I guess I'm in this coordinate chart. Just check it out. Let's think. So I should still be here. But because now that so because now this value is smaller, at the next blowing up, I'll have to, the center will be the intersection point with the previous exceptional divisor. Okay, so there's only 2 more to go. Okay, so let me drop the colors. Please go. So because now 1/10 is less than 1/5, the next center will be here, and there's only one more. So this will be U prime over U1 prime squared, comma U1 prime Q over squared. So now the values are 1/10, 1/10, and the last one. blowing up is so this is the very last exceptional divisor. These two curves got separated, but now there is a choice. So now, yeah, I won't write out the coordinates. U prime square comma. Now it's u. No, it's
There's
u.
no square on the free one, right?
Sorry.
There's no square on U prime on the free one. On the second coordinate.
Here, you mean? Here, wait. Right, there's no square, sorry. And so here on the other hand, we have q1 to the prime to the fifth divided by and so now there's a choice because I haven't told you what the evaluation looks after this. So in the case where mu is equal to mu1, in our old terminology, the center will be the entire exceptional divisor. Or another option is if there exists Q2, the next equal number such that Q2 is strictly greater than U1 of Q2, then this Q2 would have a very explicit form, would be something like Q1, I guess Q1 to the fifth minus C2 to the 16. And then this constant C2 would be, then the center would be a closed point on the exceptional divisor, and it would be determined by this constant C2. Okay? And then, so you can continue. It either might continue to infinity, or you might stop at some point. If at some point you stop, and the center of the variation is the entire exceptional divisor, such variations are called divisorial. Well, I'll give some other characterizations of them in a little while. Or you might, the center might remain a closed point forever. You might continue blowing up forever and get an infinite sequence of blowing ups. In any case, so we can start this. So let me call this 0, 1, 9. This might be defined to infinity. And at each point we have a center of the relation. Of course, the centers, it's easy to see the centers must map to each other. And there are many things. For example, one nice thing about this, about the sequences, I have the relation of birational domination among the local rings. So remember I said that the prime example of birational domination is when you blow up a point and take a point in the preimage. So here, all these local rings are mutually dominating, and so forth. So that's one nice aspect that happens in dimension 2, which is a little bit more complicated in higher dimensions. Here, if you take the union of all these local rings, you obtain a maximal element with respect to relational domination. And that's exactly the valuation ring. So in the end, you obtain all these guys are dominated by the valuation ring, and it's exactly the limit to the union of the local rings. So okay, so I think probably this is what I'll do next time is what is shown in the handout, try to explain what happens in full generality for completely general valuation, how to completely classify valuations by the group. Well, maybe, the last thing I'll say today is that instead of drawing all these curves, which is kind of messy, it's much nicer and much more clear to draw the dual graph. So that's, again, I think that appeared in several talks, certainly probably with another idea. So dual graph means or an edge for each intersection of curves. In my case here, all the curves are smooth, rational, all the intersections are transverse, so it's very nice to represent my graph. So let's draw the graph here. The graph consists of just one vertex. Here, the graph consists of two vertices connected by an arc, by an edge. Here, it's three vertices. There is also usually we also put the minus the self-intersection number of this curve, but I won't insist on that because it's not, that's usually considered to be a part of combinatorial data. The point is that I'm associating a kind of combinatorial variant to the relations. So here it looks like this. So this is beginning to look like what you have on the handouts. This is the globe graph here. Okay. Okay, so here I guess here this and no, this and yeah, this is right. This is right. Okay. Here it's and so, and as is explained in the, as is shown in the handout, we can classify also the length of each branch. I'll explain this in more detail next time. And this graph is completely described by continued fractions. First by 3 halves, and then by 5 halves. Okay, so I'll do the general case tomorrow. Are there any questions?
What are the schemes?
Ah,
Schemes.
no, the only reason for the schemes was to say, you'll see more of them later, but the only reason was to say that to be able to talk in a unified way of the center of valuation as a point. In all cases, the center of valuation is a point, right? Even when it's even when it's a curve, I consider that as a point. And this, maybe for surfaces, I didn't have to do this, but in higher dimensions, in the general case, it will be much nicer. Otherwise, you would always have to, everything, language will become much more messy because I want to take the schemes. At some point, I'll take projective limits of schemes. Then it's really important that the center is a point in the sense of scheme, not in the sense of classical varieties. Okay, but here for the surface case, I didn't have to mention schemes. Okay.
When you have this case of result evaluation, when the procedure stops at final place, it seems you do some blowing ups. So it seems that you do some kind of a resolution of singularity of the valuation.
That's right. That's right. So, that's absolutely right. It's a very good question. To be precise, what I do is, you see that I have my sequence of key polynomials, which I defined earlier. So in this case, for example, I have u, and I have q1. Let's assume we also have q2. So precisely, what we do is these key polynomials are plane curve singularities of increasing complexity. And what we do is we successively resolve singularities. So the first combinatorial package consists of desingularizing Q1 by a combinatorial procedure. Then, as you see, Q1 turns into a coordinate. Its split transform turns into a coordinate. And then we do the second toric procedure, which consists in desingularizing Q2. And so on. So I should maybe give credit. Bernard Tessier is one of the big proponents of this philosophy. And also there's an old paper of Oka and Akampo where they explain the resolution of singularities in terms of not sequence of blowing ups, but toric packages. Each combinatorial package is a single toric transformation. Okay, but this might go on forever. You might have infinitely many key polynomials, so you have to do this infinitely many times. And that's precisely the relation. That's precisely what I'm interested in. Is precisely the relation of the resolution of singularities. So we want to understand resolution of singularities as successively desingularizing key polynomials.
Then the exceptional divisor that will appear of the composition of all of this blowing up, it's how I could see it geometrically.
Well, I mean, there is a description. I mean, this is a special case of the general description. I'll give the general description tomorrow. But I can draw it, so, I mean, what do you describe? I can draw a picture, I can draw a graph, I can tell you exactly what the length is and, you know, what numbers appear. And, well, if you go on to infinity, then it's not a, it's no longer an
And
algebra.
tomorrow eventually you could give some example of non-divisible relation?
Of course. Yeah, so, but even here, yeah, I'll do this in more detail later, but even here, imagine that, okay, divisorial means we stop at some finite stage and the center is the exceptional divisor. But non-divisorial is everything else. For example, suppose this happened to, the value of this happened to be an irrational number. Irrational, then you would have to go to infinity. I'll classify all the possibilities next time. Or suppose this was, suppose our group was Z2 with lexicographic ordering, and suppose that actually all these values, so let me stick a 0 in front of all these values, okay? And suddenly this one would have value 1,0. Again, then you would start going to infinity. Think even, maybe for next time, think of the example. Suppose, what would happen if I have mu of v 0,1 and mu of u 1,0? What kind of blowing up sequence does this give me? Right? It's kind of obvious, right? That so in coordinates it would be v comma u, then v comma u over v, then v comma u over v squared, and this goes on forever, right? It's v u over the n. Right? So the corresponding dual graph would be just a straight line, a bamboo. And so it means first you have one exceptional divisor, then you have two, then you have three, and so on. And just go up to infinity. So I'll classify, in the next 2 lectures, I'll classify all the possibilities and explain the relation with rank and rational rank and so forth.
More questions? No?